Hi boys and girls, this is lecture 4.6 in Unit 4. The topic, optimization problems. This is part 1 of a two-part lecture regarding this topic. Another way to describe optimization problems is to use the phrase applied maximum and minimum problems. One of the most common applications of calculus involves the determination of minimum and maximum values. It is very useful to know things like greatest profit, least cost, least time, greatest voltage, optimum size, least size, greatest strength, and greatest distance. As usual, calculus to the rescue. Now, I am going to connect what we're going to discuss today to our previous lessons, the ones in particular involving curve sketching. We found that setting the first derivative equal to 0 was the way to discover maximum and minimum points on the curve. Well, doesn't it make sense that if we have a curve that's actually modeling a real-life situation, that setting the first derivative of that function equal to 0 will yield maximum and minimum quantities for that situation? For example, let's say that you're measuring some sort of quantity that's growing or decaying over time. We would construct a mathematical function which models the growth or decay of that function, and perhaps we would like to know when is the maximum or minimum of that quantity going to occur. Well, once that function is constructed, taking the first derivative and setting it equal to 0 will yield those maximum and minimum results. So again, let's say we have a function that's modeling profit. Aren't we always going to be interested in where the greatest profit is? That function that models profit for this particular situation, take the first derivative, set it equal to 0. Or cost, perhaps we want to minimize cost. There's going to be some sort of mathematical function which models cost for some company or whatever the situation. Take the first derivative, set it equal to 0. Least time, maybe we want an optimum volume, or we want a smaller size quantity, etc. In each of those cases that you take the mathematical function that is modeling the quantity, take the first derivative, set it equal to 0, and it yields the maximum or minimum of that quantity, which is pretty exciting. Let's get started. All right, this is a typical scenario. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? If we think about it, we would probably realize that there are many manufacturers out there designing containers for their product. They have to consider the dimensions that make sense for their product, but they're also probably going to want to minimize the cost of making the container. Well, that's a surface area situation, because surface area represents the materials that are going into making that container, and we would want to minimize surface area to minimize the cost of the materials. But of course, we do have to consider the dimensions of the product that is being produced. In this case, we're told already that the surface area must be no more, no less than 108 square inches. How do we maximize a box, the volume of a box with that surface area? We could come up with some trial and error situations, letting X represent some quantity and Z representing some quantity, coming up with several scenarios in which the surface area is 108, and then determining which volume is the greatest. Or we could use calculus, and in one shot we could take the first derivative, set it equal to 0, and determine exactly where the maximum volume is going to be. So that's what we're going to do. Now notice that in this situation we have the volume being maximized. We always have to determine from the problem which quantity is being maximized or minimized. We construct an equation which will give us that quantity, and we call that our primary equation. In this case, since we're maximizing volume, the volume of this box would be x times z, x squared z. This is our primary equation, and this is the function we're going to take the first derivative of and set equal to 0. However, there is one small problem. We can't have two variables in our primary equation. We need one variable, and so then we look to any other information that's given in the problem in order to make that happen. Notice that they told us that the surface area is 108. We could set up a surface area equation which relates those same two variables together, and based on that information, solve for one of the variables in terms of the other. Once we do that, we could substitute that quantity back into our primary equation, resulting in an equation that would only have one variable. Well, in this case, our surface area is just the surface area of a rectangular prism, except for one small little tweak. There is no top to this box. So often we would take our normal geometric formula, which would be the surface area of a rectangular prism, the area of all 6 faces added together, and we make sure that if there's any tweaking that needs to be done to the formula, we would do so. In this case, the fact that there's no top means that the surface area formula will be slightly different. Yes, we will need the area of the base of this box, which is x squared. We will need the area of the 4 sides of the box, which in this case is x times z in all 4 cases, but we won't need the area of the top. So the surface area for this box is x squared plus 4xz. Now remember, the only numeric information we were given in the problem is that surface area is 108. When we set 108 equal to x squared plus 4xz, we have set up a situation in which we'll be able to solve for one of the variables in terms of the other. If I subtract x squared, that gives me 108 minus x squared equals 4xz. And then dividing both sides by 4x, I end up with 108 minus x squared over 4x is equal to z. Now, this is valuable. The secondary equation was useful to me because I had a problem in my primary equation. But now that I have used the secondary equation to solve for one of these variables in terms of the other, I can rewrite my primary equation and substitute for z the quantity that I found, 108 minus x squared over 4x. Now let's do a little bit of simplification. Notice that one of these x's here cancels with this x here, leaving just x to the 1. That's going to need to be distributed to the numerator, so I'll end up with my volume function will be 108x minus x cubed over 4. And because I would rather use the power rule than the quotient rule, I'm going to rewrite this as two separate fractions, 108x over 4 minus x cubed over 4. So my volume function will be 27x minus 1/4 x cubed. Now I have my primary equation ready to go. I'm going to take the first derivative and set it equal to 0. So our first derivative will be v prime is equal to 27 minus 3/4 x squared. Now we know that setting the first derivative equal to 0 will yield maximum and minimum values. So we set 27 minus 3/4 x squared equal to 0. If I add the 3/4 x over to the other side, I end up with 3/4 x squared equals 27. Multiplying both sides by 4/3 in order to get rid of that fractional coefficient gives me x squared is equal to 36. When I take the square root of both sides, I get plus or minus 6, but of course we know in this situation we're not going to have a negative dimension, so x is equal to 6. Notice that we know exactly now how to maximize the volume of this box. Let x be 6, and then we can solve for what z needs to be. That means we would take 108 minus x squared, which is 36, over 24. This becomes 72 over 24, which is 3. So we'll let z be 3 and x be 6, and we're guaranteed that that maximizes the volume for a box that has 108 square inch surface area. So that's how you use calculus to get this information. Now, one little cautionary note. After we've done all this work and we get x equals 6, we may be so happy we may stop there. But go back and look to see what the question is asking for. It is saying, what dimensions will produce a box with maximum volume? Make sure that you go ahead and solve for z then, because they want both of the dimensions. It might say something like, what will the maximum volume be? In that case, go ahead and multiply x times z to get the maximum volume. So just be sure that you're answering the question that was posed in the problem. Here are some general guidelines for solving applied minimum and maximum problems. First, identify all given quantities and quantities to be determined. In the last example, we were given surface area and we were to determine maximum volume. If possible, make a sketch. Always make a sketch, boys and girls. That always makes it easier to come up with the equations and functions that you need. Second, write a primary equation for the quantity that is to be maximized or minimized. In the previous example, that was the volume equation, since we were maximizing volume. Number 3, reduce the primary equation to one having a single independent variable. Remember, you can only have one variable in the primary equation. Now, since you're using general geometric formulas, sometimes there's more than one variable. There could be several dimensions which comprise that equation. That means you might have to use a secondary equation relating the independent variables of the primary equation. So you use the secondary equation to solve for one variable in terms of the other. That way you can go back to your primary equation, make a substitution in order to get down to a single independent variable. The fourth step, determine the feasible domain of the primary equation. This makes sense because we're talking about the real world. The domain is not going to be all real numbers. We have finite quantities that we're using, so we should determine the values for which the stated problem makes sense. And then finally, step 5, determine the desired maximum or minimum value by using the first derivative. Here's another example. Here we're going to find minimum distance. The question says, which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? So notice that I have the graph sketched here and the point 0, 2. And then hypothetically, we could say we could be talking about this point here and this point here. If we were trying to guess which point on this parabola, or which points on this parabola are closest to 0, 2, maybe it's here. We don't know exactly, we're guessing. But what we're going to do is say whatever that point is, we're going to assign it the variable xy. We're looking for an xy that is closest to 0, 2. Since we're minimizing distance, we're going to use the distance formula. Remember, it looks something like this. Distance will be the square root of, subtract the y values, y2 minus y1, quantity squared, and then subtract the x values, x2 minus x1, quantity squared. Add those two squared quantities together and take the square root, and you have the distance between 2 points. So that would give me the distance between 0, 2, and any coordinates that I choose on this parabola. But what I want to do is find the exact point at which I would have the minimum distance. Again, I could use trial and error. I could find some points that are on this parabola, maybe 0, 4, maybe negative 2, 0, and see, is that the shortest distance? Is this the shortest distance? I could do this a long time because there's an infinite number of points on this parabola, right? Or I could use calculus, and I know that I can take the first derivative of this distance formula and it will tell me exactly what x or y coordinate will be the one that's closest to the point 0, 2. So let's do that. Let's go ahead and set up our distance formula using these two sets of coordinates, 0, 2 and xy. This means I'm going to have the distance between 0, 2 and some random point on the parabola will be, subtract the y values, I'll say y minus 2, quantity squared, plus, and then subtracting the x values, x minus 0, quantity squared. Now let me simplify this a little bit. I have the square root of y minus 2 quantities squared, and of course x minus 0 is just x, so this will be x squared. This is what I'm going to minimize. Of course, I have one small problem, two variables. I need a single variable in order to take the derivative of this function and find the minimum distance. So I go to my secondary equation. What is it? It is the equation of the parabola. This equation also relates this same x and y value that I'm talking about. So notice it's already solved for y. Y is equal to 4 minus x squared. I can just replace y in this formula with 4 minus x squared. So let's rewrite this now with that substitution. I'll have now the distance is equal to 4 minus x squared minus 2 plus x squared. And when I simplify a little bit, oh sorry, that quantity is squared, I'm going to end up with a negative x squared plus 2 quantity squared plus x squared. Now let's FOIL this out and combine like terms. You may have to go off to the side and do this. Let's do negative x squared plus 2 times negative x squared plus 2. That gives me a positive x to the fourth minus 2x squared minus 2x squared plus 4. And then combining like terms, I get x to the fourth minus 4x squared plus 4. And then remember, I'm going to be adding x squared to that. So let me just go ahead and show what the simplified argument of the radicand will be. It's going to be negative 4x squared plus x squared. That's going to give me x to the fourth minus 3x squared plus 4. So now my distance formula is the square root of x to the fourth minus 3x squared plus 4. I'm ready to take the first derivative. I can rewrite this function as d equals x to the fourth minus 3x squared plus 4 to the 1/2 power, and use the chain rule to take the derivative and set that equal to 0. However, it's really not necessary to take that entire derivative, because isn't it true that if I just minimize the quantity under the radical, this part, I'll minimize the radical in general. So let's just take the derivative of the argument of the radical to save ourselves a little time. The derivative of the radical itself is more complicated and it's not necessary. So as I take the derivative of what's under the radical, I'm going to end up with 4x cubed minus 6x. Let's set this equal to 0 to see where the max and min values occur. Remember, you may not add over the 6x and divide by x. That will eliminate a root. What you must do instead is factor out 2x. That leaves 2x squared minus 3 equals 0. And remember that setting this first derivative equal to 0 yields maximum and minimum values. So as I set 2x equal to 0, which gives me x equals 0, we know that this is a local maximum value on this curve. However, when I set 2x squared minus 3 equal to 0, that's going to give me 2x squared equals 3, which leads to x squared equals 3/2, which gives me x equals plus or minus the square root of 3 over 2. The square root of 3 over 2, positive and negative, because there are 2 points on the parabola where we're going to have that minimum distance. Now let's find the y values associated with plus or minus the square root of 3 over 2 by going back to the original function. Y is equal to 4 minus, remember we're going to take the square root of 3 over 2 and square it, and it doesn't really matter if we have plus or minus here, because of course squaring it makes it positive. This means I'm going to have 4 minus 3/2. 8/2 minus 3/2 is 5/2. So the two ordered pairs that are the closest to 0, 2 on this parabola are positive square root of 3 over 2, 5/2, and negative square root of 3 over 2, 5/2. Now think about it, boys and girls. If we had used trial and error, how long would it have taken us to actually try the square root of 3 over 2? chances are it would have taken a while. But using calculus, the first derivative, setting it equal to 0, solving for the values that give you the max and mins, we got it right the first time. That's awesome. All right, one more example. We're going to find minimum area. A rectangular page is to contain 24 square inches of print. The margin at the top and bottom of the page are to be 1.5 inches, and the margins on the left and right are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used? Okay, I do have a diagram drawn here. We're talking about, in this case, an area of the print, and I'm going to use this rectangle to sort of demonstrate what we're talking about. They tell us in the problem, even though this isn't exact, you kind of get the idea, that the actual print on the page is going to have dimensions 24 square inches. So I'm going to let the length of the dimensions of just the print be x, and y will be the width of just the dimensions of the print. Then it says the margins at the top and bottom of the page are to be 1.5 inches. So in addition to the variable x, then I'm adding 1.5 on top and bottom for the margins of the page at the top and bottom. And the margins on the left and right are to be 1 inch. So to the width that is represented by y, I'm adding a 1 inch margin on the left and a 1 inch margin on the right. What should the dimensions be so that the least amount of paper is used? Well, let's think about this. If we're talking about the actual page, we're talking about the area of the entire page. That is what we need to minimize because we want to use the least amount of paper possible. So we're going to minimize an area of that page. So let's write the formula for the area of that page. The width is going to be the y that I've chosen to designate this variable, plus 1, which will be y plus 2. The length is going to be x plus the margin at the top and the bottom. 1 plus 5 plus 1 plus 5 is 3, x plus 3. This equation represents the area of the page. Again, I have a problem. I can't have two independent variables in my primary equation. I need one. So I need to find some sort of relationship here, a secondary equation, which will allow me to solve for one variable in terms of the other. Notice that in the original sentence, or the first sentence of the problem, I'm told that the area of the print is 24. So I can use the area of that section, the area of the print, which is xy, just this section times this section. I can set that equal to 24, and that will allow me to solve for one of the variables in terms of the other. It doesn't really matter which one I solve for. I'll say that y then is equal to 24 over x. So this was my secondary equation. Here is my primary equation. Yes, they're both area formulas, but one is area of just the print. I had the numeric value for that. And then of course the other is the area of the page. Since I'm minimizing the area of the page, that's my primary equation. This was the secondary equation. Useful because it allowed me to solve for one variable in terms of the other. Now let's rewrite my primary equation, making that substitution. A is going to equal now 24 over x plus 2 times x plus 3. Let's go ahead and FOIL this out to make it as simple as possible before we take the first derivative. We're going to end up with 24 over x times x is 24. 24 over x times 3 is 72 over x. 2 times x is 2x. And 2 times 3 is 6. Let's rewrite this. We're going to have 30 plus 72 over x plus 2x. And then finally, I'm going to write this so I can use the power rule. And I'm going to say this is 30. I'll put plus 2x and then plus 72x to the negative 1. Now I'm ready to take the first derivative. I think this calls for a change in color. So let's do this up here. A prime will be 2 minus 72x to the negative 2. Let's set this equal to 0 in order to solve for a max or min value, a min value in this case. 0 equals 2 minus, and let me rewrite this now, as 72 over x squared. If I add that over, I get 72 over x squared equals 2. When I cross multiply here, this will yield 72 equals 2x squared. Dividing both sides by 2 gives me, and sorry for the torturous path that this equation is taking, 36 equals x squared. When I take the square root, of course, not worrying about the negative root here, I get x equals 6. So the way to minimize the dimensions of this page is to let x equal 6. That means, of course, since the area of the print is 24, that I need to let y equal 4. When x equals 6 and y equals 4, I minimize dimensions of this page. But let's make sure we're answering the question. What should the dimensions of the page be so that the least amount of paper is used? Remember, x is the length of the print. Y is the width of the print. That's not the width and length of the page. So for my final answer and for a final change in color, and trying to find some room here for my final answer, the length of the page will be x6 plus 1.5 plus 1.5, which will be 9. So this will be 9 by, and then of course y, which is 4, should be added to 1 plus 1, which is 2, and that's going to give me 6. So my final answer, 9 by 6. That's it for today's lecture. Units of measure. You never know when these might come in handy. You're welcome. God bless you, boys and girls.